Your heating bill is not a utility charge. It is a monthly lease payment on a system engineered to require your continued participation whether the temperature outside is 40 degrees or 4. Think about what happens the moment you stop paying. The gas gets cut, the electricity gets cut, the thermostat goes dark. The furnace, which cost you $4,000 to $8,000 to install, becomes an expensive piece of sheet metal bolted to a duct system that now moves nothing. Anjay, you didn't buy a heating system. You bought access to a heating service, and the distinction matters the moment the service stops. Picture January, 3 days into a grid outage. Your insulated walls are doing their job. The cold is being held at the perimeter, but the interior temperature is dropping at roughly 1 to 2 degrees Fahrenheit per hour in a well-sealed house, which means by hour 48 you are below freezing inside. Pipes burst, food spoils, and the family moves to one room and burns through every blanket in the house. Now picture the same house, same walls, same insulation, but with a floor that has been storing heat since the fire was last lit 2 days ago and is still radiating at 68 degrees. That floor exists. It has existed for more than 2,000 years. The Romans built it, and then the rest of the world forgot it existed and sold you a furnace instead. The forced air heating industry doesn't survive on one-time sales. It survives on the service contract, the filter replacement, the annual tune-up, the eventual compressor failure, the duct cleaning, and the 15 to 20-year replacement cycle that begins the moment your previous unit dies. Every component in a modern HVAC system is rated for a finite operational life. The heat exchanger, the blower motor, the ignition module, the thermostat, Hypocaust, and each failure point is an opportunity for a billable service call. The system is not poorly designed. It is precisely designed, just not around your long-term independence. It is designed around your long-term participation in a revenue model that requires the grid to be on, the gas line to be pressurized, and the technician to be reachable. Remove any one of those three conditions and the system is inert. Roman engineers solved the central heating problem before 100 BC and did it without a single moving part. The hypocaust, spavan from the Latin hypocaustum, meaning heat from below, was a raised floor system in which columns of fired clay tiles, called pilae, supported a suspended stone floor above a hollow subfloor chamber. A furnace called a praefurnium was built into one exterior wall and fired continuously with wood. The superheated air and combustion gases rose through the hollow chamber. I traveled under the entire floor surface and exited through hollow ceramic flues built into the walls. The floor above absorbed and stored that heat, then radiated it steadily upward into the room at a surface temperature that could be maintained between 85 and 120 degrees Fahrenheit for hours after the fire died down. Roman bathhouses, private villas, military barracks, and administrative buildings across Britain, Germany, North Africa, and the Middle East use this system. In climates ranging from sub-zero to desert heat, and examples of intact hypocaust chambers have been excavated at more than 400 separate archaeological sites. Heat does not distribute evenly in a room unless you force it to. This is the foundational engineering problem that every heating system has to solve, and it is the problem that most modern systems solve badly. Forced air heat warms the air and moves it, but warm air rises immediately, which means the thermal energy you paid for migrates to the ceiling, where it benefits no one except the attic. The occupied zone of a room, the lower 4 feet where people actually live, stays comparatively cool while the upper 4 feet near the ceiling bakes. Radiant heat bypasses the air entirely. It transfers energy directly from a warm surface to any cooler surface in line of sight. The same mechanism that makes you feel the warmth of a fireplace on your face from across the room even when the surrounding air is cold. A heated floor is the most efficient possible delivery geometry for radiant heat because it is the largest possible surface area at the lowest possible position. Every object in the room, every person, every wall absorbs radiant energy directly from below. The specific heat capacity of stone, the material Romans used for their floor surface, is approximately 840 joules per kilogram per degree Celsius. A stone floor slab 10 centimeters thick across a 40 square foot room contains enough thermal mass to store and release heat for 6 to 10 hours after the heat source is removed, maintaining a surface temperature warm enough to keep the room above 60 degrees Fahrenheit indefinitely in moderate cold conditions. Think of a traditional stone bread oven, the kind used in every European village from ancient Rome through the 19th century. You fire it for 2 hours with hardwood, then let the fire die completely, Seal the opening and slide your bread in. The bread bakes perfectly for the next 40 minutes on stored heat alone. There is no flame, no ongoing fuel consumption, no temperature dial. The stone absorbed the energy, and now it is spending it at exactly the rate the thermal physics dictates. The Hypocaust floor is that bread oven turned horizontal and placed beneath an entire building. You fire the pryfernium, the stone charges, the fire can go out, and the room stays warm for the rest of the day. The genius of the Roman design was not the heated floor alone. It was the path the heat took to get there. The pilae columns supporting the raised floor created a plenum chamber, a sealed horizontal airspace roughly 2 feet tall running under the entire floor plan. When the pryfernium burned, it didn't push heat directly into the room. It pushed superheated combustion gases into that plenum, where they spread laterally in all directions simultaneously, contacting the underside of the floor slab across its full surface area before exiting through the wall flues. This meant the entire floor heated evenly, while with no hot spots over the furnace and no cold corners at the far end of the room. The wall flues served a second purpose beyond exhaust. As the hot gases rose through the hollow ceramic tubes embedded in the walls, they heated the walls from the inside out, creating a secondary radiant surface that enclosed the room in warmth from 3 directions: below from the floor, from 2 sides from the walls, and convectively from the warm air the floor surface generated at ankle level. These modern radiant floor heating systems replicate this principle almost exactly, replacing the plenum chamber with embedded water pipes or electric elements, at installation costs between $10 and $20 per square foot. The Romans built theirs from fired clay, stone rubble, and timber, materials available within 5 miles of any building site on 3 continents, and achieved equivalent thermal output. The materials list for a functional Hypocaust-inspired radiant floor, insert in a single room, is shorter than you expect. You need fired clay bricks or concrete blocks for the pilae columns, standard 4 by 8 by 2 inch bricks at roughly 50 cents each from any masonry supplier. You need a stone or concrete slab for the raised floor surface, flagstone works, poured concrete works, dense ceramic tile set in mortar works. You need refractory cement for the joints, rated to at least 2,000 degrees Fahrenheit, available at any hardware store for under $20 a bag. And you need a heat source for the pryfernium. A small wood-burning rocket stove with an exterior exhaust port is the functional modern equivalent, or a sealed propane unit vented to the outside. The total material cost for a 10 by 10 foot room Hypocaust is between $200 and $400 depending on your slab material choice. Begin with a clean, on level subfloor surface, compacted earth, concrete, or existing stone. Mark a grid across the entire surface in 12-inch squares. Each grid intersection is a pilae position. Build each column by stacking 3 to 4 bricks with refractory cement between each layer to a finished height of 8 inches. Use a spirit level after each layer. A leaning pilae column will create an uneven floor slab above it, and an uneven floor slab cracks under thermal expansion. Space every column identically. Uniformity is not aesthetic here, it is structural. Allow the refractory cement to cure for a minimum of 48 hours before applying any load. This is non-negotiable. Refractory cement that is not fully cured will crack under thermal stress, compromising the entire chamber seal. For steps 4 through 6, lay your slab material across the pilae tops, beginning at the wall farthest from your intended heat inlet and working toward it. I use a continuous bead of refractory cement at each pilae contact point and at every joint between slab sections. The plenum chamber beneath must be airtight on all sides except the inlet and the exhaust flue. Any gap in the perimeter wall allows cold air infiltration that will defeat the thermal build. Cut your exhaust flue port through the exterior wall at floor level on the opposite side from the heat inlet, sized to match your chimney pipe diameter. Seal all perimeter gaps with refractory mortar. When the system fires for the first time, the floor slab will take approximately 90 minutes to reach operational temperature. Do not attempt to accelerate this by overfiring the pryfernium, as rapid thermal expansion in an uncured system will fracture your slab joints. Build the heat slowly, hold it, and let the mass do its work. Archaeological thermal studies of intact Roman Hypocaust sites, specifically the bathhouse complex at Wroxeter in England and the villa system at Fishbourne in West Sussex, have measured residual heat retention in the floor slabs at ambient temperatures between 75 and 95 degrees Fahrenheit, measured at points up to 14 hours after the last firing. Modern thermal imaging of the Vindolanda military site Hypocaust showed the original clay pili retaining differential heat signatures nearly 2 millennia after their last use, a direct measure of the material's thermal stability. Ciao! Engineers at the University of Bath's Center for the Study of Ancient Documents ran computational fluid dynamics models of a reconstructed Hypocaust chamber and found that the Roman plenum geometry achieved between 78 and 84% thermal efficiency, meaning 78 to 84% of the heat energy generated by the pryfernium was successfully transferred to the floor slab and walls, rather than lost to exhaust. A modern forced air gas furnace operates at between 80 and 98% combustion efficiency, but loses 25 to 40% of that output to duct heat loss before the air reaches the living space. The Romans, with fired clay and stone, match the effective delivery efficiency of equipment designed with computational modeling and precision manufacturing. The cost comparison requires only one set of numbers. A Medra mid-range gas furnace installation in the United States costs between $4,000 and $8,000, has an operational lifespan of 15 to 20 years, and carries annual maintenance and fuel costs averaging between $1,200 and $2,400 depending on climate and home size. Over 20 years, that system costs between $28,000 and $56,000 in total. A Hypocaust-inspired radiant floor system for a single primary room costs between $200 and $400 in materials, requires no electricity to operate, no gas line, no annual service contract, and no replacement cycle. The floor is the heater. Stone does not have a warranty period because stone does not wear out. The ruins at Bath, England have been standing for 19 centuries. The Hypocaust chambers beneath the Great Bath Complex were excavated beginning in 1878 and found to be structurally intact, with the original pili columns still bearing load, the floor slab still level, and the wall flue channels still clear. Archaeologists at Pompeii documented 47 separate Hypocaust installations in the city buried by Vesuvius in 79 AD, ranging from modest domestic versions to the elaborate multi-chamber systems beneath the Stabian baths. On every single one of them functioned on the same principle: mass, geometry, and a fire. No circuit boards, no pressure regulators, no licensed technicians. 2,000 years of evidence that the physics works is the longest-running performance test in the history of building science. The forced air system in your home right now has an average operational lifespan of 15 to 20 years, requires a functioning electrical grid to ignite, a functioning gas network to fuel, VRNAN, and a certified technician to repair. 4 dependencies stacked on top of each other, any one of which can strand you in January. Either you understand that heat is a material property of dense objects and you build accordingly, or you keep leasing access to warmth from a company whose business model ends the moment the grid does. The Romans didn't hope the supply chain would hold. They built the heat into the floor. That knowledge has been sitting in the archaeological record for 2,000 years, available to anyone willing to look at it. Now you've looked. Build one room this year. Share this with someone paying $400 a month to stay warm in a house that will go cold the night the grid fails.